I've got a piecewise function on the board. F of x is x squared plus k. K here is some unknown constant, and our task is going to be to find the right constant. We're given that formula if x is less than or equal to negative 2, and it's x minus 1 if x is bigger than negative 2. And our task is given to us in this box here. We're supposed to find a value of k so that f of x is continuous everywhere. Now, to the left of negative 2, it's going to be continuous because x squared plus k, for any constant k, is just a polynomial, and we know that polynomials are continuous. Okay. To the right of negative 2, it's x minus 1. That's a linear function, and lines are continuous. What I have to worry about is what happens at negative 2. So what I need is, if this is going to be continuous at 2, I need that f of negative 2 is equal to the limit as x approaches negative 2 of f of x. That what I get at negative 2 is equal to what I expect at negative 2. But because this is a piecewise function and I'm using different rules on either side of negative 2, rather than evaluating this directly as a two-sided limit, I'm going to need to split this up into the limit as x approaches negative 2 from the left of f of x, and the limit as x approaches negative 2 from the right of f of x. So even though the definition only requires that two things be equal, the limit and the function value, the way I'm going to work this out is by setting three things equal to each other. The function value has to equal the limit from the left, and that has to equal the limit from the right. If those three things are equal, my function will be continuous at negative 2, and we can see by inspection that it's continuous everywhere else. Okay, so let's just evaluate those three things. So if I look at f of negative 2, well, the rule I use when x is negative 2 is this top rule. So that would just be negative 2 squared plus k. So that's going to be 4 plus k. Okay, let's take the limit from the left. The limit as x approaches negative 2 from the left of f of x would be. Now, if we're coming from the left, then again, we're using the top rule. So although I can't always replace f with x squared plus k, if I'm coming at negative 2 from the left, I can. So I can say this is the limit as x approaches negative 2 from the left of x squared plus k, which I would evaluate by simply plugging in negative 2. So that's negative 2 squared plus k. That's 4 plus k. Now I sort of get for free that these guys are equal to each other because I was using the same rule to evaluate the function value and to evaluate the limit from the left. Now let's take the limit from the right. Now if we're coming from the right, we're going to be using this bottom rule. So now, instead of replacing f of x with x squared plus k, I'm going to replace it with the formula for this line. So we're taking the limit as x approaches negative 2 from the right of x minus 1. Now I can evaluate that by simply plugging in the negative 2. So I'm going to get negative 2 minus 1. I'm going to get negative 3. Okay. Now, in order for my function to be continuous at negative 2, I need these things to be equal to each other. So if I say 4 plus k has to equal negative 3, I can see that k would have to equal negative 7. With that value of k, this function will be continuous everywhere. Now what I just did is I attacked this problem sort of algebraically. I just worked with the formulas for the function. I could also think of this a little bit more graphically. This is a piecewise function. I know that we change rules at negative 2. Okay. Now, to the left of and at negative 2, we're going to have a translated parabola. This is just my function x squared moved up k if k is positive, and down the absolute value of k if k is negative. Okay, so I'm going to have part of a parabola at and to the left of negative 2. To the right of negative 2, I'm going to have a line. In fact, it's going to be the line x minus 1, which I know just has a slope of 1 and a y-intercept of negative 1. Okay, now if my function's going to be continuous, I don't want this picture. If my function's going to be continuous, what I'm going to want is that that hole where the line leaves off gets filled in by the point where the parabola starts. I want this picture, not this picture. If I have this picture, I've got a jump discontinuity. If I have this picture, even though I've got sort of an abrupt change, I still have a continuous function, because what I get is what I expect from both sides. So if I'm thinking about it more graphically, I can say the value of the point on x squared plus k has to equal the value of the whole on the line x minus 1. Okay. So I want the point and the whole to be in the exact same location. Okay. Now, this is really doing the same work that we just did, because the value of the point, since we're actually just using this function, I get that by simply plugging in negative 2. So that would be negative 2 squared plus k. Okay. Now there, that's both the value of the function and the limit as I come in from the left, again, because I was using the same rule for the function value and for the function to the left of that. For the value of the whole, that's just going to be the limit as x approaches negative 2 from the right of x minus 1. So this is going to be 4 plus k equals negative 3. And again, k equals negative 7. Okay. So whether you're thinking about it more algebraically or geometrically doesn't particularly matter, but I think it's nice to see the geometric interpretation of that algebra.